huge supernova explosion in that case. Now, I think what they're also pointing out is that in general, not only is energy conserved, but momentum is conserved as well. And so they're just kind of pointing out that so here, I guess this would be before, but then after the reaction, what's going to happen is that everything has to occur in such a way that you end up basically conserving both energy and momentum, I guess, during this whole process right here. And so I guess in this case you have maybe something like this, and okay, I see they show two different scenarios. So this before, in this case, kind of straightforward, and then this will be after the reaction where the X component is conserved, but you have a Y component presumably because of these reactants that are taking place. But in this case, what's happening is that if the, I think what they do is they're considering the case where maybe the X component velocity is such that you end up getting scattering in opposite directions, essentially in the X directions, but then also similarly in the Y direction as well, in the scenario B, I guess they illustrate right here. Okay, okay, so they pointed out for low energies of E less than O. By the way, and I also wanted to point out the barrier height, the Coulomb barrier, I think I may have been not quite correct. I said it was around 20-something kiloelectron volts, let's say for deuterium and so forth, and tritium, but it may not be quite right. The barrier itself may be a lot bigger, but I remember reading that, and I think it's because of this quantum tunneling process, that the energy of the actual deuterium and the tritium nuclei coming in need to be, if I remember, around the 25 to 50, somewhere around 25 kiloelectron volts during the fusion reaction, and that minimum, I think, might have been just, okay, that's the minimum needed to be able to quantum tunnel through the barrier and whatnot. So the barrier itself may actually be significantly higher than what I talked about there. And then, of course, again, you can translate directly to that to a temperature, which tells you, okay, what temperature would be needed for the fusion reaction to take place when we get into, let's say, talking about that. Okay, so let me oh, okay, that's interesting. In a high state of excitation, which means that if it's in a high state of excitation, of course, it's going to be unstable, basically, and so it can either emit, either alpha or beta or gamma. In some cases, it might be a gamma ray that might be emitted, and as the thing is dropping down to a lower, let's say to the ground state for that. And so, so here, I think this, I suppose very, very crudely, we can sort of think of our old particle in a box model, except, but what they're showing, I guess, would be these, again, these energy levels are going to be in the mega electron volt range. And so conceptually, here they talk about entrance channels and exit channels right here. But conceptually, I guess one of the ideas is that when one of these guys was in a very high excited state after the, let's say, some reaction, if it then decays back down to what might be the ground state for that particular system, it can end up emitting a pretty energetic gamma ray photon that might be in the tens of mega electron volt range and whatnot. Okay, I wanted to get to radioactive transfer. So there's actually methods by which they can actually synthesize heavier elements too, like using neutron capture and so forth. I wanted to go ahead and get to the one that talks about things that might be used for energy production. So, for example, in the case of a fission reactor, so this is one of the ways that we could actually use that for power generation. So it turns out that I'm going to point out that in, I think, your most common fission reactor plant, U-238 is not sufficiently reactive, I guess, to use by itself for fission. So typically, we have to use, and it turns out that U-238 is actually the most abundant form of uranium. And so U-235, which is this one right here, is actually a much lower level of abundance than U-238. But you need to, so you have to what they call enriching the uranium. So you have to create a larger concentration of this compared to what you would have under normal circumstances. And in order to do this enriching process, it's actually not such an easy thing to do. What they do is they actually, I think they create a compound of uranium with fluoride. So it's like uranium hexafluoride, if I remember correctly, which is actually a gas. And then what they, and the only thing that's going to distinguish these different isotopes are the masses. And so what they do is they put this I think it's the uranium hexafluoride, into these extraordinarily high-speed centrifuges. They have to be ridiculously high speed. And what happens is that you just get some fractionation of the constituents of the U-238 versus U-235. That's actually the hardest process, the hardest part of the entire process of actually making something that could be used for a fission reactor, or of course you could also use it to build a bomb too, a fission bomb. That is why there's a lot of hoopla about Iran in particular, having all these hundreds or thousands of high-speed centrifuges that are used to enrich uranium and produce this guy right here, because again, once you can produce enough of this guy, you can either use it to build a fission reactor, or you can use it to build a bomb, basically. And now apparently there's a lot of subtleties involved in how this thing actually takes place, because so the actual mechanism, I guess, by which the reactor ends up, why you get a runaway chain reaction, is that once you're able to get the thing started, in other words, get this thing started, you're giving off neutrons. So notice that you're giving off these are the reactants, these are the products right here. So you have this guy very excited, kind of unstable right here, which is undergoing fission to produce these two guys right here, giving off 3 neutrons. Now what happens to these guys right here? Well, if you have it set up above some critical mass, you can see these guys are going to come right back and hit some of these guys, essentially be absorbed by some of these guys, creating more of these and triggering more of these guys and more of these guys. So it's basically a chain reaction that takes place. And so if you just have enough of this in a critical mass, how does that chain reaction proceed? It basically proceeds in the form of a bomb, of a nuclear bomb, essentially. Now, the way I think the early atomic bombs were designed was that so they did some calculations. I don't know the details of how you calculate, okay, what is the critical mass that you need for the thing to actually just blow up and have it be an explosive reaction. So what they did is they had a couple of different ways. One would be I think some kind of implosion to get the thing up to some critical mass. The other was simply having a rod of U-235 or something enriched uranium coming down into another shell of U-235, so that the whole thing would end up going above the critical mass in the early atomic bombs. Now, what about a controlled fission reaction, like in a nuclear reactor where you don't want it to blow up? So that's where you put it in and you have these control rods. You're trying to control the rate at which this reaction is taking place. You don't do it in a very explosive way, but you have the control rods and so forth. You just kind of slow down the reaction, I guess, so that you have enough of these guys coming in so that it happens on a continuous basis, but that it's not happening in an explosive fashion, but you're still releasing energy in the process because you're giving off a certain amount of kinetic energy. Now these two guys right here themselves, I believe, are quite radioactive, and so that is why they say, okay, that's what they call the waste, the so-called waste. And I think they could further decay into other waste products as well. And so that's one of the problems that we haven't completely resolved, in the sense that I think right now that most of the waste is pretty much just kept right there on the site at the fission reaction reactor, and that's what actually was the problem, like during the tsunami and the Fukushima reactor problems and so forth, is that, well, a lot of the place where they stored the waste got affected by the tsunami and so forth. So there were a whole slew of issues that are really problematic. And then, at any rate, some of the earlier fission reactor designs also have problems with potential, if you don't keep the thing cooled and so forth, you get a meltdown and whatnot. So there are more modern designs, I guess, that have been developed, and so I think there are ways that one can try to eventually, or actually even now or in the near future, make smaller scale and much more stable and safe nuclear reactors, which actually may turn out to be one of the important mechanisms to try to come up with a way of having a very low or close to zero or low carbon footprint, for example. And let's see, okay. And here's the thing that's kind of interesting also, is that they actually find that the liquid drop model apparently is a nice way of kind of visualizing what happens during this fission reaction process. And so apparently they were able to kind of do some quantitative estimates about, okay, what would be the rates at which these would take place. And so so when the neutron comes in, it kind of creates this kind of elongated, unstable nucleus. It then kind of splits up into these two droplets, and then in the process you end up giving off 3 neutrons during that fission reaction. And of course they have a certain amount of kinetic energy at the same time, of course, when these things are given off. And and plus gamma rays too. It says, okay, typically carrying away all the 30 to 40 mega electron volts of kinetic energy in this process. And then here they talk about, if at least one neutron on the average results in another fission, the chain reaction becomes critical. So if you slightly exceed that, then you're basically above that critical, let's say it might be above the critical mass in that case. So this would be when they talk about the critical mass right here. So it's subcritical versus critical, and then finally supercritical. And then they says an atomic bomb is an extreme example of a supercritical fission chain reaction. And you can see U-236 is the thing that is above that line of stability. And so that's the one that's extremely unstable. So once the U-235 absorbs the neutron forming U-236, that is very, very unstable. And so it undergoes that fission reaction then. Okay, so then, and I think this is where the control rods come in. In other words, yeah, here we go. So control rods regulate the absorption of neutrons to sustain a controlled reaction right here. And so that's what you would use in a nuclear power plant, essentially, would be these control rods to try to control the rate at which this thing is taking place. Oh, and now here's the other thing that's kind of interesting too, is that if you look in terms of energy density right here, see that's actually one of the things that potentially makes nuclear reactions potentially very attractive. It's just the incredible energy density. You look at the amount of energy contained, which can be released, let's say, by burning 1 kilogram of coal, for example, or a barrel of oil. So you have, it'd be 30 megajoules, I guess, for 1 kilogram of coal. Now you compare that to reacting 1 kilogram worth of uranium, and it's 100 terajoules, so 10 to the 14th joules of energy that can be released in that case. And that's just because, again, each tiny little nuclear reaction that's taking place is releasing in the tens of mega electron volts worth of energy, whereas if you compare that to what happens when you're burning carbon to produce CO2, it's going to be in the several EV range, in several electron volts range let's say, per molecule in the case of coal. And then you say daily fuel requirements for a, okay, this would be the daily fuel requirements for a 1 gigawatt power plant, an entire trainload per day for coal, a tanker a week for oil, some humongous amounts of natural gas, or just 3 kilograms of uranium. And that's, by the way, that is why military submarines tend to be powered by nuclear reactors, because that's how they're able to stay underwater for months on end, is because they actually use a nuclear reactor that's can keep the thing powered for a very, very long, months or maybe even years at a time. Okay, so moderator used to elastically scatter the hydrogen and reduce their energy, and hydrogen in water, carbon, graphite, and beryllium are all good moderators. Now there's also, nowadays, or there's some of the other reactors that they're talking about are molten salt reactors. Again, I don't know the details of why would molten salts be more attractive, but I think supposedly, I guess the molten salt is something that would not, where you could not have a regular meltdown taking place like you would with an ordinary reactor. In other words, if the thing just kind of gets out of control, it'll just automatically shut down, supposedly, on some of these other designs. And so I think the like your conventional reactor, the problem is if the water, let's say, boils off, basically you're using it also as a coolant as well, then the thing can just kind of get out of control and melt down. So there's a lot of things you have to keep active in order to keep the thing from melting down. And if whatever it is you're using to keep to actively keep the water in there to slow down the reaction, if that fails, then you can get a meltdown. And I think that happened in Fukushima after the tsunami and whatnot. Okay, and then here they show kind of an old photograph, I presume, but these guys are inserting the control rods into this massive thing right here. And so, and the idea is you want to control the rate of reaction by basically controlling the number of control rods that you're putting into this thing right here. And so, now, oh, okay, by the way, okay, how do they get the energy out? Well, it's actually kind of a simplistic way. It's really not much different in principle from what you would do just burning natural gas or coal, I suppose. It's basically all you're doing once you have the reaction taking place is you're just literally heating up water and then maybe boiling it and converting it to steam and then using that to drive a turbine. So once you actually have the reaction, the actual process by which you use it to generate electricity then becomes pretty much the same as you would for any other type of like natural gas type of power plant. So that'd be your turbine right there. I guess this would be another maybe scheme where you're trying to avoid any of the water used in this part of it be contaminating the other water that you have in the rest of your system right here. So you have some heat exchanger right here. But you can see that conceptually the actual process of generating electricity then is pretty straightforward once you've actually created the heat in the reaction. Okay, several training reactors. There might be one up at Texas A&M, possibly. I'm not certain about it, but I think there might be. Okay, so here we go, 3 Mile Island, Fukushima in 2011. Some examples of problems that took place. Chernobyl was another big one. That was another one that took place, which released quite a bit of radiation into the atmosphere. Breeder reactors where you're actually breeding plutonium, which can then be used itself as a fission reactant material. And so it can basically give you a very high supply of fissionable material, but the problem is that, and the other nice thing is that because you can use U-238 and put it to use, then you can use of a great deal more of the available supply of uranium in order for these fast breeder reactors. The downside, well, the problem is that you end up creating material that can be used for weapon production right there. Okay, so now this is the one where I will have a couple of exam problems, pretty simple ones. I think that'll be like the last two Thornton and Rex exam problems will be from this particular section that goes into fusion. Fusion would be perfect. It'd be like a perfect ideal energy source if we can succeed in reaching that break-even point in a controlled way. We have done it in bonds. The problem is we haven't done it in actual controlled reactors yet. And the reason, of course, part of it is because of the fact that you have to have extraordinarily high temperatures, and you need some. And the problem is, how do you contain something that's going to be in the, let's say, millions of degrees of temperature, and be able to control that type of reaction? And so I think what I will do then, I think this is probably a good point, because I want to make sure I don't get locked out. This is probably a good point to break off for now. So I'll continue on this particular topic next time, and then I will also maybe start walking through some of the take-home exam problems and whatnot, either next time or the time after that.
Hard water. Remember in World War II, I think there was a mission or something to destroy the Germans' production of hard water or something. Was that pretty much the controlled reaction?
So when did you say hard, or was it heavy water?
I think it was heavy. Oh, I'm sorry, heavy water.
Heavy water?
Yeah.
So I remember. Well, there was a. I remember there was a mission that the Germans had a heavy water facility. I guess they were trying to produce heavy water where you're just creating it's like D2O essentially. And I don't remember if it's because D2O is a better way of controlling nuclear reactions than H2O or exactly what. I'll have to read up on what. In other words, why do we want to use heavy water instead of regular water? By the way, I think most reactors that we use now I think they do call them light water reactors. I think they are light water reactors, but there could be some advantages of heavy water. And I remember there was even a movie that came out quite a long time ago about the Allies actually went in to wipe out this one heavy water plant in Norway. That I guess after the Nazis occupied Norway, they went in and they blew up this plant. I guess, and there's quite a clandestine mission that took place during World War II. But I would have to read up on exactly, okay, what would be the advantages of heavy water versus light water? Because the disadvantage is a lot more difficult because then you have to produce, you have to make it basically, and get all this D2O.
The 10 questions that you brought up for your final, could you say that again? You have 10 questions, several of which have several parts. A few of them have several parts. And then there's going to be one or two that's going to have box scenario, particle in the, well, not, you're going to use box to solve it. Expand on that, please. Okay,
so again, for the final exam, take-home exam, and I'll go over this in a little bit more detail, either next time or one of the subsequent lectures. The first 4 problems are ones that I came up with myself. Like the first one is going to be something involving matrix methods, and then it'll be something you've seen before, but just kind of a slightly different twist perhaps, where you're going to be throwing in a perturbation into the particle in the box problem, and then what you're going to do is you're going to compute both the diagonal and the off-diagonal matrix elements of the Hamiltonian, and then going through and just taking a two energy level approximation. So you just exactly diagonalize this 2x2 matrix, and then try to figure out what are the new energy eigenstates or energy eigenvalues in that case. The next one's going to be pretty similar, but instead what you'll do is you'll actually go to 4 energy levels, but then use time-independent perturbation theory. So it'll be kind of similar, but you'll be using time with the same perturbing potential, if I remember correctly. You'll be using time-independent perturbation theory to figure out the new energy levels, energy eigenvalues in that case. The third one is going to be a harmonic oscillator problem, where I'm going to be throwing in a time I think it's an oscillatory electric field or a time-dependent electric field as your perturbation. So that's where you're going to be doing a little bit of time-dependent perturbation theory. So you want to look up the slides on time-dependent perturbation theory. The fourth problem, again, another nice particle in a box problem, but this time squeezing the length down to like a few femtometers. So it's going to be as a way of getting a very crude approximation of a certain type of different type of nuclei, essentially. So the idea is that you're going to see, okay, wow, these energy levels are really humongous. Now when you squeeze this down into the femtometer range, and so there'll be and then I think one of the latter sections of that problem will involve actually trying to estimate the Fermi energy for something involving like 20 neutrons. And so you'll just be kind of counting the energy, you'll compute the energy levels. You just fill these up 2 at a time and then figure out what's the uppermost energy level that's filled. If you do it 2 at a time, spin up and spin down, and that'll basically be your Fermi energy in that particular problem. And then the last, I guess I call it problems 5 through 10, are 2 problems each from chapters, Thornton and Rex, chapters 11, 12, and 13. So this is kind of a smattering of Thornton and Rex problems then. And the last 2 problems, the very last 2 problems are going to be on this topic about fusion right here. And so that'll be from chapter 13 then. And that, I hope that'll be enough to keep you busy without being too overwhelming. But you'll have the entire rest of the semester almost, up until we get. I need to give the grader enough time so he can grade them. So maybe before the actual end, before the very end of the semester, but I'll check with the grader. And the idea would be, okay, I want to give the grader enough time, but at the same time give you enough time to actually work the problem. So I'll figure out the due date after I talk to the grader and so forth. Otherwise, I hope everybody has a good weekend, and I'll see everybody on Monday.